Good morning, everybody. I continue my series of lectures on zero-sum problems. So this is the penultimate lecture. One point of the lecture will be to discuss the set-based problems, so where we consider sets rather than sequences. But before I do that, I still wanted to say some things on the Davenport constant, but in some sense also by extension on a general phenomenon. So we saw various results that established the value of the Davenport constant. And the question arises somehow what goes wrong for the groups where we do not yet know the Davenport constant. Does anything go wrong, or is it just a method of the proof that does not work, this algebraic argument here? What does go wrong for other groups? What do I mean by other? So for instance, for groups of rank 3. So we saw the results for, we saw the results for groups up to rank 2. So what's with groups of rank 3? And for instance, what's in some sense a simple group of rank 3? For instance, one can consider C2 plus C2 plus C2n. And here one can ask oneself, so what is the Davenport constant? And how can one determine it, or why do the proofs we saw up to now fail? Or maybe they don't fail, maybe we just have to see that they work. So, but it will turn out that, at least for this group, the value of the Davenport constant is still as expected, but one has to work a bit more for the proof. But if one continues a bit, then actually things break down. So consider this, and so if n is even, then we are in the rank 2 like case. So because if n is even, then I actually can write it as C2 plus C2 plus C2 plus C4 times m, and then C2 plus C2 plus C2 plus C4 is a group of this form that arose in this result where I called the groups rank 2 like, because the exponent here is large relative to the rest. So assume n is odd. And maybe subjectively, it's, in some sense, it's not very clear how arithmetic considerations even come into play. If one has a more, so to say, I mean, it could also be one considers these coordinates, and whether it's 32 or 34 is maybe not crucial. One could also assume this, but actually, as it turns out, this difference is very important in some cases. Already, although not in this case for the result, it turns out that the C2 plus C2 plus C2n is still equal to C2 plus C2. So this would be 2n plus 2. So let's put theorem, and let's give a proof. This result is actually very classical. It's in already in one of the first papers on the subject from the end of the 60s, and there it's attributed to Bayern and van Lint. Very good. But the paper itself is not written by Bayern and van Lint, but it's the oft-quoted paper by Van Emde-Bros that contains this result. So how does one proceed? It's always the same method in a way, so let K be subgroup isomorphic to Cn such that C2 plus C2 plus C2n, so that is okay. And now let S be a sequence over C2 plus C2n of length 2n plus 2. So what will we do now? We do the usual thing. We know that 2n plus 2, we can write this as 2n minus 6 plus 8, 2 times n minus 3 plus eta of C2 R, 3. Thus, considering the image of the sequence in this group, we see that there are subsequences S1 up to Sn minus 2 of S with disjoint, so it's always subsequences of S with length Si at most 2, and sigma of Si, so the sum of Si is an element of K, which is an element of K, which is a cyclic group, because it's a zero-sum sequence here, so this means just that. Now, there are basically two cases, but maybe let's have a brief look. So what would we actually want? So we have n minus 2 such sequences. So we get a sequence of lengths. If we consider the sequence of the sums, as we did frequently here, then we have already n minus 2. So but the Davenport constant here is n. So n minus 2 does not suffice. So I want to reach the size of the Davenport constant here. So in some sense, I would need 2 more elements. So can I find 2 more? Well, how many are left? So at least 6 are left. So if I've taken here 2n minus 4 at most, so 6 elements are left. Among 6 elements, I definitely can find 1 more zero-sum subsequence in C2 to the R, because the Davenport constant here is 4. But I can only find 1 maybe, not 2. But what I can say is this is somehow, but maybe under some conditions I still can find some. And so the first case is, so if the remaining remaining sequence. So this is S, and exclude this if the remaining sequence has length at least 7 or contains 0 or an element more than once, then one can find two more zero-sum subsequences. Let's say two more subsequences with sum in K. So zero-sum subsequences in the quotient group. Excuse me, has length at least 7 contains or let's call this T and such that or pi of T contains 0 or an element more than once then. And by pi I mean here C2 plus C2n, so the projection to this quotient group. So the repeated element or the 0 is not in the sequence itself, but in the image in C2 to the 3. So yes, because if I have 0, I extract 0, and that's fine. If I have the same element twice, I take these two elements and 5 remain, and 5 is larger than the Davenport constant, so I can still find one more. And what's it with 7 elements? Yeah, among 7 elements, and if I do not have 0, it means I have all the non-zero elements of the group. Then I can definitely find 3 that sum 0. I take those 3, and the 4 that remain will also still contain a zero-sum subsequence, because that's exactly the Davenport constant. So okay, and we are done. So assume the length of P of T is 6. I mean, it won't be smaller than 6. This is clear, is 6. And all the elements are distinct, and non-zero. Excuse me?
What is the pi of T?
The pi of the, it's the, I denoted by pi the projection to the quotient group. Maybe I should, yeah, I think in other lectures I've called it phi, but this. Yes, but so now I understand the question better, because the phrase is written doesn't assume E6 and all the elements in so yeah, 6 elements, they're all non-zero. So without loss, no. Without loss, assume the E1, E2, E3, E1 plus E2, E1 plus E3, E2 plus E3, where C2 R is E2. in some sense, it's not even without loss. I could also say I choose the basis of this group in such a way that it's this. So, but why can I do this? Well, 6 non-zero elements means just that there is one element missing. But in some sense, all the elements of an elementary 2 group, they are equivalent. So there are no, except, yes, all non-zero elements in some sense equivalent. So they are all just as good. And so I can say it's the sum of 3 basis elements. So I choose the basis in such a way that this is true. And now let's call the corresponding elements in T. I'll denote them G1, G2, G3, G1, G2, G1, G3, G2, G3. So that these elements remain. And here, among these 6 elements, it's actually, I cannot find disjoint zero-sum subsequences, 2 disjoint zero-sum subsequences anymore, but I can find plenty of zero-sum subsequences. E1, E2, E1 plus E2, E1, E3 is 1, but also a different one, E1 plus E2, E1 plus E3, and then E2 is 3, so there are plenty of possibilities for finding zero-sum subsequences. So let us assume, so now let U in T be a subsequence with sigma U in K. And now, so if the sequence sigma S1 up to sigma Sn minus 2, so these were the sequences which are chose, and sigma U is not zero-sum free, we have a zero-sum subsequence of S. So if this sequence is not zero-sum free, so if it has a zero-sum subsequence, then this also induces in the usual way a zero-sum subsequence of S. However, this sequence is already very long, so its length is n minus 1. So the only way how it is not how it is zero-sum free is that all the elements are equal. The only way how a sequence of length n minus 1 in a cyclic group of order n does not yet contain a zero-sum subsequence is that all the elements are equal. So sigma U is equal to some G0 in K for, well, let's say, so there is a G0 in K thus there is a G0 in K such that sigma U is equal to this one G0 for each for each u in T with sigma u in K. So for all the subsequences I can choose here, I have this condition. And the question is, and conversely, if this condition holds, then that's also fine in some sense. Then likely it should actually be the entire sequence zero-sum free. So the question is, can I make it so that I have this condition? But let's see. But let's check. Let's see the sequences we have. What do we have? We have G1, G2, G1, 2, G1, G3, G1, 3. And we also have G2, G3, G2, 3, and we have G1, 2, G1, 3, G2, 3. So these sequences, so these are 4. So one has to read it like this. So one sequence, another sequence, yet another sequence. So all these sequences, and we also have a different type, G1, G2, G2, G3, G1, G3, G1. This does not match the usual pattern in which I wrote it. G1, 3, and so here we have G2, G3, and here, and then what's the missing? Well, G1, 3, G2, 3, and then here I would have G1, G2. So I have these 7 possibilities for choosing a zero-sum subsequence here, a subsequence with sum in K. And let's call this, maybe let's call this U1, U2, U3, U4, and let's call this V1, V2, V3. And now, what can one note now? If we look at this here and this here, then we see it's the same elements. So here we have each of these elements with 2 indices once, and then and we have each of the elements with 1 index twice on both sides. So we note so here. On the one hand, we know, on the one hand, we need that sigma u1 is equal to sigma u4 is equal to sigma u1. So they are all equal to this G0. And so this G0 is non-zero. I should say that. On the one hand, we need this. On the other hand, we have that U1, U2, U3, U4 is equal to V1, V2, V3. But this is a contradiction because it gives that 4G0 is equal to 3G0. So G0 is equal to 0. In some sense, there are too many conditions for these 6 elements. There are too many possibilities to combine them to fix their sum. Yes, so thus S has a zero-sum subsequence. And yes, so this finishes this. Okay. So this result, it just shows, okay, there are more groups that fulfill this equality. So maybe one just has to work harder for more general groups. But in some sense, one also, one can sense somehow that it's maybe actually more complicated than in the case of rank 2 groups, because there's an additional argument needed. One needs to know something in addition. What did we need to know in addition? In particular, we needed some information on the structure of zero-sum free sequences in the cyclic group. And in fact, by now, one can have this result here in more generality. So the proof is complete, so we know this, and there's a more general version. More generally, theorem. So for n1 divides n2, one has that the Davenport constant of C2 plus C2 n1 plus C2 n2 is equal to C2. So one has this. So this is also a classical result under assumption on zero-sum sequences over rank 2 groups. Under an assumption on zero-sum sequences over rank 2 groups. Maybe that's just a classic result under a technical assumption, and that's by now this is known. And more specifically, what was the technical assumption? So basically, what does one need? One needs some knowledge that replaces. One needs some knowledge that replaces this here. And there are various ways to do it, and in particular, so the actual technical assumption that was given is what then became known as property C, which is a result on the structure on the extramal examples with respect to the eta constant. It's mostly, maybe not the most intuitive thing why this plays a role, but one could also impose the same. One just has to understand the structure of extramal zero-sum free sequences in groups of rank 2. So it also works with this, and this is then in more close analogy to this here. But technically, it was, at least at that time, easier to derive it from this other property. But in the end, also it turned out that these two properties are, at least for CP squared, more or less equivalent. So this is this entire context of property C, property B, and these results on structure inverse problems of zero-sum sequences over rank 2 group. So if one knows these things, then one can conclude something on the Davenport constant here. And another important keyword is the so-called, for those that know it, the new invariant. I won't recall this here, but it's the issue is, I mean, here we can fix, we know that the sequences all will have a fixed sum. In the general case, it's not true that they have a fixed sum, but the sums, one can conclude that the sums all have to lie in one fixed non-trivial coset, which is actually good enough for running this precise same argument, because then one gets that, one just does the addition with the cosets and gets a contradiction. And one can actually, so the question is, do all the elements that are not yet represented by the elements that we constructed lie in one given coset, and one can introduce a constant based on this, the new invariant, and study it, and in some sense, so the argument runs. So if one has this result, which one can obtain, if one knew the other thing, then everything works out. But by now, it's all known unconditionally. And so one knows the Davenport constant also for these types of groups, but still somehow results for groups beyond rank 2 are somewhat sparse. So there are some more results. I won't give all the results, but there is also not a huge amount of those. Now, as I already alluded to, sometimes it's also, in a way, it's not surprising that things become more difficult, in particular if one wants to show this equality D equal to D star, because at some point things really actually break down. So in the sense that what about in general? So of course it will depend a bit on the n, because if n is a power of 2, we know it all the time, and also if n is divisible by a sufficiently high power of 2, depending on r, we also know it's equal the Davenport constant to the standard lower bound, but it turns out that a Davenport constant of C2 to the 4 plus C2 n is strictly greater than D star of C2 4 plus C2 n for n 3 odd. Yes, so for even no. And so if it's divisible, if n is divisible by 4, we are even under the result we already saw, but even for even 1, it's not. So how can one show this? Well, one has to write down an example. So to say of a sequence that is long enough. How long a sequence do we need? So what's the size? What's this? This is 2n plus 4, so 2n plus 4. So we would need a zero sum free sequence of length two n plus 4. And where might it come from? Well, let's write let's look at this situation here. So, if we run the same argument, definitely, so at least if the n is large. If we do the same thing we do all the time with the cyclic subgroup, then if the n is large, we definitely can extract quite a number of short zero-sum subsequences, and we get a bunch of elements in the cyclic group, and then something will remain. So maybe one possibility would be more or less to do what we had to do here, and then maybe we arrive at a situation like this. But since we have more space, so we are not in an elementary 2 group of rank 2, but maybe of a larger rank, we can arrange things that it works that it actually works out in the way we need it, and we do more or less exactly this. So let us write the group. So let us write the group as E1 plus E2 plus E3 plus E4 plus G. So with the idea that the order of the EIs are 2 and the order of G is equal to 2n. Sorry, 2 of course. And now how can we construct the sequence? So in some sense, likely we will still need one element often to not have a too large sum set, or at least this could be a start. So let's take the G here often. How often could we take it? Well, maybe also not too often. At least we want to keep somehow one spot, so to say, in the cyclic group spare, so we can at most have n minus 2 sums in the cyclic group, so we can have at most n minus 2 sums in the cyclic group, so we can have at most 2n minus 3 times this element. So let us start with G to the 2n minus 3. And then we need 7 more elements. 7 more elements. And one thing which we have with these elements, and if we have these 7 elements, then and we pass to the group where we quotient out the cyclic subgroup of order n, so the subgroup generated by 2G, then these elements, also we can also look at even quotient out by G itself, so then all these sums should just fall precisely in the slot, so to say, that is still open, which would just correspond to 2G. So these 7 elements, they can have zero-sum, they can have subsequences whose sum lies in this cyclic subgroup, but we need to be able to control the sums. So the situation is like here. Here we had 6 elements, and we knew all these combinations, they would have to have the same sum. but we could not manage it here. Here we found the contradiction. But maybe we can manage it in this situation. And let's forget the G. Let's just work with the E1, E2, E3, E4. And so let's try to choose the elements in such a way that we can control all the subsums. Or all the sequences with the so 7 elements. And I just write it in E1, E2, E3, E4. And also, I mean, let's start with E1, E2, E3, E4. Basically, we can always start with this because basically all the elements are the same. So we can choose basis. And now what could we add? We want to have 7 elements such that we can control all the sums. And one thing one can do is one can pick, for example, one can add E1, E2 plus E2 plus E3, E2 plus E3 plus E4, and E1 plus E2 plus E4. So these are 7 elements, and why do I choose these ones? Well, if one checks, so this gives a sum of length 4, this gives the sum of length 4, this gives the sum of length 4. Is there anything else? So if I take 2 of those, then I need to complete with 2. So this also gives the sum of length 4. And if I take all three, then I need one more element. So this also gives a sum of length 4, and there are no other possibilities. So here for these 7 elements, so if you choose it like this, then each 0 sum subsequence has length 4. But these are proper zero-sum subsequences if I write it like this. So this is not good. So I need also a G component. And what should the G component be? Well, the G component should be that the sum corresponds to 2G. So I need an element. I need that. I mean, in principle, I can add different things here, but if I add different things, then likely it will be harder to control the sum. So it's easier to add the same thing everywhere. And what do I add everywhere? So what I add everywhere is an element such that 4 times this element yields 2G. So I want 4 to the minus 1, 2G here. So actually, I mean, this is maybe a bit risky to write it like this. Does this make sense? Well, more or less. Let's write it in a different way where it's more obvious that it makes sense. So this is what I want. So but if I write n plus 1 over 2 G, then if I multiply this with 4, I get, if I multiply this with 4, then it's 2n plus 2g, and 2n is the order of g, so then it's gone. So, and n plus 1 over 2 definitely makes sense because the n was precisely chosen to be odd. So here we need that n is odd. Recall n is odd. So with this sequence, it works out. This is a sequence of length 2n plus 4, which does not have a zero-sum subsequence. So the trick was to choose over C2 to the 4 a sequence where one can control precisely the length of the zero-sum subsequences. And this idea is very versatile and also works in other contexts. And there's a recent paper by Zhao Liu, who wrote his thesis with Gao, and he worked on these problems and gave various constructions related to this. But I mean, this construction, this precise form was already known, but he generalized this considerably and also clarified the conceptual meaning, I think, in the sense that it's really, it's really about controlling the length of the zero-sum subsequence. Maybe just a passing remark, this is also, some of these things are related to problems that arise in coding theory, for instance. So one can interpret this in a certain sense as a code. So the zero-sum subsequences correspond to the code words, and then every code word here, every non-trivial code word has length 4. So one might look in this direction if one wants to find other constructions. So one important point here is that, at least in this construction, we actually use that n is odd. Because if n wasn't odd, then I could not choose all the time the same element. I mean, I could choose different elements for different element I could choose different completions here for the various elements, but in the end, things just would not work out. So for this group, one actually has this. And a thing I want to stress is, in a way, there are many such examples. It's not a question mark. So for instance, there are Geroldinger Schneider, for instance, Geroldinger Schneider gave various constructions. And more recently, Zhao Liu. So his work is very recent, and I'm not even sure if it already appeared, but I think so. Well, it should by now. I would have to check a precise reference. Excuse me, I did not do this before, but so he talked about it already 1 or 2 years ago. So the thing is, that's actually a frequent phenomenon that one has this. And in a way, it's possibly even surprising if one looks at it like this, that it always holds for B groups. Because, I mean, okay, here we use it's odd, and if the order is a power of 2, then this does not work. But in some sense, we could, even if we could have 100 coordinates maybe here, and why doesn't it work that there's no reason, so to say, in some sense, that we only do this construction for length 4 subsequences. I mean, we could maybe also do it for length 5 subsequences if we had more dimensions, and then it would work out, also modulo 2 on the left-hand side. So it somehow, if I look at it from this direction, I do not find it very intuitive anymore that it's even always true for B groups. But I mean, manifestly, it's true for a B group, which likely, definitely is due to the fact that it's easier to find constructions like this or good constructions like this, where the length one admits is a multiple of the order and not just whatever. And so that's the situation. So maybe, so there are many such examples. So what would be main open problems for the Davenport constant? So there are two questions basically. Does D, C, and R equal to D star C and R always hold? So for any N and R, so for groups of this form, and maybe also does D, G equal to C star G hold for groups of rank 3. Why rank 3? Because for rank G greater or equal to 4. So the constructions that are known start from rank 4 onwards. Here we have rank 5. So for rank 2 it's known. Rank 3 would be open. So this is what I wanted to say on the Davenport constant. So since there is still some time left, I can at least start with the set-based constants. So said I wanted to talk about set-based constants in this talk, but now spend all the talk with the Davenport constant. So set-based constant. So this is really a new chapter. So this is set-based. Maybe in a sense it's the 5th chapter. Set-based constants. For instance, there's the so-called Olsen constant, so Olsen constant of G, noted O of G, sometimes also Olsen OL of G, because the O of G might be confused for something else. So it's the smallest K such that each subset or each set in G of cardinality at least K has a zero-sum subset. So this is the Olsen constant. So the set version of the Davenport constant. And sometimes technically it's more convenient to work with square-free sequences rather than sets, but maybe to give the definition now it's more intuitive to talk about sets. And then there's the Hubbard constant. So this, we already saw both names. So Olsen with early work on the Davenport constant and Hubbard for the work related to what we call now the Erdős-Ginzburg-Sieve constant, so Hubbard constant. So it's just a denoted G is the small theorem same, but then has a zero sum. Has a zero sum subset of size exponent. So this very same definition, which I do not recall. So it's the this corresponds to Davenport, and this corresponds to and I will give some results on these constants in my afternoon talk. And maybe just a word on notation. Somebody might find it confusing. I mean, why do you call it Harvard constant and then denote it with G? So this is maybe not the most logical thing to do. But the issue is that somehow the notation existed and then the name came later. So it did not really have a name. So the notation was preserved, but the name was tacked on. And now, why was the initial notation like this? I assume simply because Harvard, in the paper, he considered the problem for sequences and for sets. And the problem for sequences, he denoted the resulting function with f, presumably simply because f is a natural name for any function, so to say. And then there was a second one, so it was g. So at least this is the way I imagine it. But then these things stuck, but the f somehow was lost because then it was more commonly notated with s, but the g remained. So this is just one anecdote regarding the sometimes strange ways of names and notations. So the notation is in a way the original notation from Hubbard's paper, but of course he did not name the constant after himself, so the name came later, and we did not modify the notation to match it. Maybe h of g would be a more intuitive notation, and maybe down the road we will switch at some point. So I will say something on these constants in my afternoon talk, which will be at 2:30 as usual.